We'll just wait for a couple of more minutes. Can you tell me if I'm audible? Is there some noise? Okay, thank you. We'll just wait for a couple of more minutes and then we'll start. Let's start. So, hello everyone, this is Tanya. I'm one of the TAs assigned to the course Aircraft Design taught by Professor A.K. Ghosh. So, we'll go over the contents or the questions of week 11, week 10, and then we'll do a few questions to help you solve the week 11 assignments and the assignments after. This will more or less be like a revision. So, let's just go over it. So this question was in your assignment 10. It is very similar to one of the questions that we have solved in the initial lectures. So let's just read the question. The total weight of an aircraft, of a fixed wing aircraft, fixed wing aircraft is given by takeoff weight is given by individual weights. That's the weight of the avionics systems of various other subsystems, the propeller, that is the propulsion device, the miscellaneous weight, structural weight, payload weight, and the energy weight of the fuel. Okay, so these are the explanations of each of those weights. So it's a propeller powered aircraft. It has the following characteristics. They've given you the mass fraction of the structure, the weight fraction of the subsystems. They've given you power to weight ratio of the aircraft as a whole, the brake specific fuel consumption, and be careful to note the units here. It's kg horsepower hour. And they've given you the propellant, that's the propulsion system, the mass fraction of the propulsion system, the L by D max ratio at cruise condition, the propeller efficiency, and the maximum range of the aircraft. Okay, and the weight of all other systems which are not denoted by the ratios. So the first question is, what is the value of fuel mass fraction? So for a propeller aircraft, we have seen that the equation for range is, was the efficiency, which is given in the question, right? Yes. So efficiency, the SFC, or it's denoted by C in the equation. So we'll just go with that, C. Then you have L by D max. Then you have logarithm of weight initial minus weight final. Okay. So the range is given here, and this is in kilometers, so we need to multiply it by 1000. So that's 6385 into 10 power 3, and the efficiency is 0.65. C, which is the SFC, it's the brake specific fuel consumption. Let's convert it into the required units. What was the unit, typical unit of brake specific fuel consumption? So it was Newton per watt second, right? Watt second. Okay. So let's just convert this kg per HP hour into Newton per watt second before we use it in this equation. So that's 0.2265 into first, then you do 9.81. Horsepower to watts is 746. This is the standard conversion that we use. There was a couple of questions in the forum, but we use 746. And then from R to seconds, we do 3600. This value will be 1.81 divided by 746 comes to 8.27 into 10 power minus 7, 746. Okay, I substitute that value here. C. L by D max is 12 logarithm of initial weight to final weight. Now when we calculate this, we get logarithm of initial weight to final weight as, just do that. .7727. Now we take the exponential and then we find this value, which is 1.9685. Now we just flip it because we know that the final weight is weight final is weight initial minus the weight of the fuel. So if we flip it, it will be easier for us to do the calculations. So let's just do that. So weight final by weight initial is 1 by 1.9685. Now we substitute this into the weight final. So what you get is initial minus weight final by weight initial is 1 by 1.9685. And you get 1 minus weight of fuel by weight initial is 1.685. This gives you the weight of fuel to be the mass, the fuel fraction. Just a second. So, can all of you just mute yourselves? Okay, thank you. So, the weight fraction will be 0.491. 0.491. That is the answer to fuel mass fraction. Okay. So, once you have this ratio, it's fairly simple. To find this ratio, we use the range formula of a propeller aircraft. Maximum range of the propeller driven aircraft. Okay, so now let's go to the next question. The weight of the aircraft in kg is, so weight of the aircraft, they mean the total takeoff weight of the aircraft. So that's WTO, this one. This is what you're asked to find out. So let's just write down that equation again. W takeoff is W avionics plus W subsystem plus W propulsion system plus miscellaneous weights plus weight of the structure plus weight of the payload plus weight of the fuel. Okay, now they've given you the weight, they've given you the weight directly of the avionics, payloads and other miscellaneous weights. So you have weight of avionics, you have the weight of the payload, plus you have this W other. Okay, so let's just write that down. W takeoff is 50 plus W subsystem plus W propulsion system plus W structure plus W fuel. Now if we are to take all of these to this side, to the left hand side of the equation, and if you have to take WTO common, you get 1 minus W subsystem by WTO minus W propulsion system by by WTO minus weight of the structure by WTO minus weight of fuel by WTO is equal to 50. Now this WTO and the W initial of the previous case are the same. So that's the takeoff weight, initial weight, it's all the weight of the aircraft when it's about to take off. Okay. So we need to find out this W takeoff. W takeoff is, so what is this value? Subsystem mass fraction is 0.051. Propulsion system mass fraction is given here, 0.05. Structure's mass fraction is 0.26. It's given here. Okay, these are the values. And the mass fraction of the fuel we just calculated is 0.491. It's 50. So your W takeoff weight is 50 divided by 5 minus 0.26 minus 0.491. So that gives you so you get something around 340.13 kgs. Okay, so that is the weight of the aircraft, which is W takeoff, which is W initial, everything. It's the same thing. Okay. So the next question is, what is the weight of the power plant in kgs? So now they've given you the power plant. Where is it? Yes. This is the propulsion system, which is the power plant. So they've given you this mass fraction. Let's just write that down. So what we have is P by W takeoff by T by W power plant propulsion system, it's the same thing. If you simplify this, you get W prop by W takeoff, which is 0.05, and what we need to find out is W prop. So W prop is nothing but 0.05 into takeoff weight, which was 340.13. So if you just multiply that, you get the weight of the propulsion system. It's around 17 kgs. So for an aircraft whose weight is 340 kgs, you need a propulsion system for this particular aircraft, which is 17 kgs. Okay, and what about the weight of the fuel? Let's just try calculating how much fuel we'll need for this maximum range. Okay, for this maximum range. So weight of the fuel was by W takeoff. This is the first thing that we had calculated, the fuel mass fraction, that is 0.491. This 0.491. So how much fuel would you need to fly this aircraft? Just multiply it with the takeoff weight, which is 340. 491. So 167 kgs of fuel. Okay, so this is how, given a ratio, you're able to calculate how much weight of fuel, weight of the structures, how much payload you'll be able to carry for the given specifications of the aircraft. Okay, so once you have the takeoff weight, once you have a gross estimate of the takeoff weight, you can calculate the other requirements based on their mass fractions. You can also do vice versa to get an estimate of the takeoff weight, like we did in the previous questions. In this question, so this is how we go about finding out the various component masses. Okay, so the next question is, what is the peak power required in HP? How do you calculate this? So they've given you P by W, right? So P by W is given here is 0.13245. They've given you directly in HP per kg, and now they asked you in HP, so this is fairly simple. So this is HP per kg, and you need power. Peak power will be associated with the maximum weight. What is the maximum weight? the weight at the takeoff. So you just multiply 0.13245. So peak will be associated with the maximum weight, which is the takeoff weight. Again, just multiply with the takeoff weight to find out the peak power in HP. So that's 0.13245. It's 45.05. Okay, so that is the peak power that the aircraft will experience. Next, they've asked you if an aircraft is cruising at the maximum aerodynamic efficiency with peak power obtained in the previous question, then what will be the speed achieved by the aircraft? Just a minute. What will be the speed achieved by the aircraft when it's flying at the peak power obtained? How will we go about doing this? Power is nothing but thrust into velocity. This velocity is what we have to find. So if you take cruise conditions, you have thrust equal to weight divide thrust equal to drag and lift equal to weight. So if you divide both sides of the equation by lift, you get an equation for thrust that is lift by drag, and you have lift equal to weight, so that is weight by lift by drag. Now substitute this here. What you get is W by L by D into V. So when you associate with the peak power, this will be maximum. So let's just find out what is the V. Peak power was 45.05. Okay, that was in HP. We need to convert it. So you do 746. Let's go with 746. So this is power divided by weight. Weight was how much? 340.13 into L by D max. Right? L by D max. Yeah, so that was 12. What is this value? Okay, the weight here should be in, you should multiply it with 9.8 when this was in kgs, okay? So with something around 120.86 meters per second. Okay, that is the velocity at which it will, velocity that the aircraft will achieve if it's using the peak power in the previous question. Okay. Now let's look over a few questions that are basically a revision of various concepts that we've studied in this course. Okay, it's fairly simple, just go with it. What is the aspect ratio for the given data? So they've given you the Oswald's efficiency factor and they've given you the drag polar. How will we find the aspect ratio? How will we find the aspect ratio? Am I audible? You can put it up in the... Okay, thank you. Okay, so how do you find the aspect ratio, AR? So you have everything that you need in this question. Guide me through it. How do I get to the aspect ratio? Okay, let's start with the drag polar. What is the standard equation of a drag polar in terms of its parameters, not in the numerical values? What is the standard equation of a drag polar? CD equal to? Okay, the equation for drag polar, not just coefficient of drag. What is drag polar? Drag polar. What is drag polar? The relationship between CD and Cl square, CD and Cl is the drag polar, right? Okay, so the relationship between CD and Cl is called the drag polar, which is given to us by this equation in this question. What is the standard form of this equation? CD equal to this is one of the basic concepts that we started with. We had done several conditions like minimum thrust required, minimum power required. Just a minute. Yes, so we had done conditions like minimum thrust required, or minimum drag, or minimum power required, maximum range, maximum endurance. There were several conditions. We had several values for CD and Cl at those conditions. How did we come to that, and what were they in terms of? What is this quantity? So if CD versus Cl square is plotted from this equation, will it be a straight line? Will it have what form will it take? CD versus Cl square. If I take CD here and if I take Cl square here, what form will it take? Just from this equation. This is equation. Just take any variable. So let's just take y equal to, what is the equation? Where CD and Cl square are the two variables. So will this equation be a parabola, an ellipse? What will it be? Yes. Yes, something like this, right? Okay, yes. So, like you said CD naught. So this is CD naught. So, its typical equation for CD versus Cl square is CD naught plus KCl square, right? This is your drag polar equation. So from this, will you be able to find out aspect ratio? What is K? Correct, 1 upon pi EAR. So E is given to you. You have K from this equation. So K is 0.03. E is 1. You need to find out AR. Very straightforward. How much is AR? What is the aspect ratio? AR is K into pi. AR is 1 by K by E. How much is this value? .61. 10.61. It's a very straightforward question. So the relation between CD and Cl is called drag polar. It takes this form, CD equal to CD naught plus KCl square. Okay, where CD naught is this intercept, it is a straight line. Okay. Next question. What is the downwash angle epsilon naught in radians? And they've given you Cl naught of the wing and they've given you the aspect ratio. How do you find out epsilon naught? How do you find this? What was the... Yes. Yes. Correct. So E, if it's not given, you take it as 1. So let's just substitute the values. 2 Cl naught of wing is 0.361 by pi 1 AR 7.1. Do we need to convert anything? Do we have to convert Cl naught wing? They've asked you the value in radians. Do you have to convert anything? Exactly. You don't have to convert anything because they've asked you the value in radians. And this entire thing should, radians as in it should be non-dimensional. Cl naught of the wing is non-dimensional. Aspect ratio, all of these If you put it back here, you get a non-dimensional parameter. So if they ask you in degrees, then you convert it to degrees. Okay, but as of now, this gives you a non-dimensional parameter which is radians. So let's just find the value. So 0.03. So this is it. So if I ask you, because our downwash angle is again with linear approximation, it is d epsilon by d alpha into alpha wing. Now if I ask you to find out d epsilon by d alpha, it's a similar formula. So it was d epsilon by d alpha is 2 CL alpha of the wing by pi EAR. Okay. Now the CL alpha of the wing, what should be the unit? Okay, but if this d epsilon by d alpha has to be non-dimensional, right? So the CL alpha wing, this equation is valid only if your CL alpha wing is in per radians. Can all of you please mute yourself? Somebody is unmuted. Thank you. Okay. So this equation is valid only if CL alpha wing is in per radians. So if your value is given in per degrees, you must convert it into per radians for this to be valid. Okay. The another equation where this was confusing was conversion between 2D and 3D. So CL alpha 3D was CL alpha 2D by 1 plus CL alpha 2D by pi EAR. Now this denominator, so this is numerator by denominator, this denominator is non-dimensional, right? But CL alpha 3D, if they've asked you in per radians, then you take your CL alpha 2D to be in per radians. If they've asked you if they've asked you in per radians, then you take per radians. If they've asked you per degree, take per degree. But this entire denominator, in this denominator, the CL alpha 2D has to be in per radians. 1 second. So the numerator can be per radians or per degrees depending on what they've asked in the question for CL alpha 3D. But the denominator has to be non-dimensional. So this CL alpha 2D has to be in per radians. The denominator equation is only valid if your CL alpha 2D in the denominator is in per radians. The numerator. Okay, so let's just see. If they've asked you, if your CL alpha 3D, they've asked you in per degrees, okay? Then you keep your numerator CL alpha 2D in per degrees. Denominator at all times has to be in per radians. Okay, so and if your CL alpha 3D in the question they have asked you in per radians, then you keep your numerator also in per radians. Accordingly, you change it, but the denominator has to be in per radians. This is all you have to remember, okay? But for these terms, since they are non-dimensional, it always has to be in per radians. If the CL alpha 3D is asked in per degrees, then you keep your numerator in per degrees. Everything else per radians. That's all. Okay? Next question. What is the neutral point location if static margin is 0.12 and CG is located at 26% of chord from leading edge? Very simple question. How do we proceed? Okay, so x bar NP minus x bar CG. Okay? So you have like what it means is you have this. It's divided by the mean aerodynamic chord. Okay? So your static margin is 0.12. So is this aircraft stable or unstable? Exactly, correct. So your x bar NP minus x bar CG is 0.26. So x bar NP is 0.38. Okay. Again, there was confusion in the forum regarding the stability, longitudinal stability. I repeat again, the only condition for longitudinal stability is that Cm alpha should be less than 0. So your Cm versus alpha graph has to look like this for stability. It can also look like this, okay, Cm versus alpha. What is the difference between these two cases? It is the y-intercept. Here Cm naught is positive, here Cm naught is negative. Cm naught has no effect on longitudinal stability. Cm naught only brings into the picture at what alpha we trim the aircraft. If your Cm naught is positive, we trim the aircraft at a positive angle of attack. If your Cm naught is, so this is trim, right? This at this point you trim. Trim is what? Where sum of all forces equal to 0, sum of all moments equal to 0. So if your Cm is 0, at trim Cm is 0, so that is this point. So if you want to trim your aircraft at a positive angle of attack, your Cm naught should be positive. In this case, this is your trim point. You have a negative angle of attack. If pass through origin, yes. But it is preferred that we trim the aircraft at positive angle of attack. It's not a requirement, it's just a preference. So for stability, for longitudinal static stability, this is the only requirement. Cm alpha has to be less than 0. That is the only requirement. There should be no confusion. Yes. Yes. Okay. One option was Cm alpha less than equal to 0. Okay. Okay. These were your options, right? Okay. Okay. At neutral point, is your aircraft stable or unstable? It is neutrally stable, but when we say stable, we require it to generate a restoring moment and come back to its equilibrium point. At neutral stability, what happens is that it defines the new location as its new equilibrium point, which is not what we want. We want our aircraft to come back to its original equilibrium point, right? So if it has to be that, then your Cm alpha has to be less than 0. Okay, so keep that in mind. Neutral stability will not be included in the stable regime. Okay. Yeah. Okay. So let's go to the next question. A wing is made of negative cambered airfoil. The lift coefficient at 0 degree angle of attack will be. So your CL alpha graph is what you need. CL versus alpha. How will the graph look? For a symmetric airfoil, how does it look? So you see, yes, passes through origin with a positive slope, right? So CL is CL naught plus TCL by T alpha into alpha, where this is positive. For symmetric airfoil, CL naught equal to 0 for symmetric. For positively cambered, CL naught is positive. CL naught, it's positive. Now they've asked you for a negative cambered airfoil. So negative cambered airfoil will look something like this. So your CL naught is negative, right? So for a negatively cambered airfoil, the lift coefficient at 0 degree angle of attack will be negative. Correct? So this is for symmetric, this is for positive camber, this is for negative camber. Okay? There we have. So it will be negative. Where do we use negatively cambered airfoil? I am not sure of the answer either, but where do we use it? do we use it? Car ground spoiler, yes, but in aircraft do we use it anywhere? Okay, I'm not sure either. Let's just look into it. We'll see. Okay. Next question. The aspect ratio of an airfoil is it finite, zero, infinite, or depends on type of the airfoil? Infinite. So aspect ratio formula is b square by s, and the span of an airfoil is infinity. So airfoil is defined as an infinite wing, whereas wing is a finite, you have a finite span. For airfoil, we assume it to be of infinite span. Okay, so your aspect ratio is infinite. Next, which of the following statements is or are correct? Read the statements carefully. The first one is, airplane with higher wing loading has higher stall speed. Is this true? What was the stall speed? Yes, correct. So stall speed formula was 2W by S. Yes, so it's rho CL. So if you have a higher wing loading, you have a higher stall speed. So the first point is correct. So A is true. Now let's look at the next one. A low wing with dihedral contributes towards longitudinal stability. True or false? Okay, anyone else? Do you have any answer? So low wing with dihedral is like this, okay, if you take the cross section. Okay, so if we have to look into longitudinal stability, we need to draw the other axis. So I will take, maybe this is the fuselage reference line and this is your CG. So if you have a low wing, it doesn't matter if it's a dihedral or not, because when we take the side view, you just have the cross section of the airfoil, take it at any point. This is the low wing airfoil, okay? So it generates, for a positive angle of attack, you have lift and you have drag. Now this lift produces what kind of moment about CG? Pitch up or pitch down? So is it stabilizing or destabilizing? Unstable. What about drag? Stabilizing. Okay. Now let's look into high wing configuration. Okay. The lift is giving you a destabilizing component and drag is giving you a stabilizing component, right? Yes. So lift gives you destabilizing and drag gives you stabilizing. This is for low wing. Okay, now let's look at high wing. So this is the lift and this is the drag and this is CG. Both lift and drag give you a destabilizing component, right? Lift and drag give you destabilizing for high wing. So compared to a high wing, low wing contributes towards longitudinal stability with or without dihedral. Okay, and compared to even a wing at the center, if it's not a low wing or a high wing, then the drag contributes nothing towards stability. Only the lift will be destabilizing. But if you have a low wing, you have the drag that contributes towards stability, longitudinal stability, right? So a low wing with or without a dihedral contributes towards longitudinal stability because there is a small drag component that gives you a stabilizing nature. Yes, lift is a lot larger than the drag, but it contributes slightly towards longitudinal stability, right? Otherwise, if you have just a wing, you need the tail to completely take over the restoring moment contribution. But if you have a low wing, there is a drag component that takes up some part of the restoring moment, correct? So they didn't say it is stable, they just said it contributes towards stability. It doesn't say that low wing is stable. It is not. If you have just a wing, yes, but there is some aspect of the low wing that contributes towards the longitudinal stability, right? I'm not saying, any wing configuration is destabilizing, but comparatively you have a low wing that is more stable, right? Or less unstable, you can say. So it just says it contributes. There is some contribution towards that Cm alpha. Correct? There is some positive contribution, there's some negative contribution towards Cm alpha. So the low wing produces one negative term, right? So the Cm alpha overall becomes more negative. So that's all this mentions. It contributes towards longitudinal stability. It doesn't say that it is stabilizing or destabilizing as a whole. It is obviously any wing configuration is destabilizing. But comparatively, low wing has a little more contribution towards longitudinal stability, a little more contribution towards Cm alpha. Okay? Okay. So point B is also true. Now let's look at the third one. A high wing contributes towards lateral stability and longitudinal instability. We know it contributes towards longitudinal instability. We just saw that. What about lateral stability? Yes, it contributes towards lateral stability. How? We have done this several times. So if you have a high wing and there is a disturbance in this direction, there's a component of velocity, oncoming velocity, that acts below this high wing, which tends to produce a restoring moment and it tends to go back to its equilibrium position. But if it was a low wing for the similar disturbance, that component of velocity will now impinge here, which will contribute towards a destabilizing moment. Okay, so high wing contributes towards lateral stability, which is this one, and contributes towards longitudinal instability, which is this one. So let me just remove this. Yeah, so this one. So point C is given by this tick and this tick. Okay. Now winglets contribute towards minimization of wingtip vortices and thereby induced drag. True, yes. So if you did not have winglets, the velocity that comes, so if this is your wing, the velocity that comes from below the wing surface and above the wing surface interact at the tip, and at that point you have large vortices generated that increase the induced drag. Now since you have a winglet, something like this, so this wingtip vortices occur only at this point now and they are smaller in magnitude. So it reduces the wingtip vortices and also the induced drag. So point D is also true. So the final answer, all A, B, C, D are true. Okay, let's go to the next question. A wing is made of symmetrical airfoil. Lift coefficient at 0 degree angle of attack will be, we just discussed this, exactly 0. So this is your lift curve slope, CL versus alpha, 0 degree, it is 0. So 0 is the answer. Next, excess power of the aircraft determines what? Level flight performance, gliding flight performance, rate of climb. What was the equation for rate of climb? Yes. So this is also equal to power available minus power required by W. So this is nothing but the excess power. This is excess power. So excess power determines the rate of climb performance. This is the correct answer. Okay. A small UAV with a total weight of 12 kg is flying with a velocity 17 meter per second at sea level. Wing area is 1.1 square meters. Find the lift coefficient. Again, very simple. How do we do this? Exactly. So you get something like 2W by S rho V square. So you have 2 into 12 1. S is 1.1, rho is sea level 1.225, and V is 17 square. 1.225. Right, so how much is it coming to? 0.604. So this is the answer. Now let's go over a question that we had seen in one of the previous lectures. So this, we had done this to find out the aerodynamic center. So we'll just briefly go over it and we'll try to find out some other quantities for this question. Okay. So this was a structure that was given to us. So what we did was we divided it into two sections, 1 and 2, and found out the area, aspect ratio, and the mean aerodynamic center for each of those, and then found out the weighted average. Okay. So the steps that we followed are, so before that we need to find out this small distance x, this distance. So for that, this 37 degrees is given to you. From that, using tan of 37, you can find out this y. You have this overall length as 800, and if you subtract the y from that, you get x. Okay, we're just going over the steps that we've already done. Then what we did was, for the first section, that is this section, we find out area. So area of a trapezoid is half sum of those sides and the vertical. Okay, so this is 675, and the sum of the other two sides is 800 plus x. X we've just found here. Okay, so we find out the area, then we find out its aspect ratio. Span is given to us, it is the 675. The area we just found out, substituted, you get the aspect ratio. Then we find this ratio, that is the root tip chord by root chord, lambda, and using that we find out the mean aerodynamic center for section 1, so C1 bar. Okay, so this is the formula, 2 by 3 CR1 into 1 plus lambda 1 square by 1 plus lambda. So C1 bar is 585.14. Now we then proceeded to section 2. So how do we proceed? What were the steps we followed? Same steps. So what do we do? First, what do we do? Area. Area was same steps as section 1. How do we do this? Yes, so we have 110 plus x, correct? X, right? This is x, this distance, correct? Into 675. So you get S2. Similarly, you do AR2. It is B2 square by S2. B2 again is 675. Then you find out lambda 2. So lambda 2 will be CT2, that is CT2 is 110, and CR2, the root chord of the second section is this, so that is x. Okay, and then you find out C bar. Okay, so this was what we did. Then to find out the overall C bar, what do? We find out the weighted average. What is the weighted average? C bar was, what was the formula? So you have the aerodynamic center of section 1, you have the aerodynamic center of section 2, but we need it for the overall section. What was the formula? No, it was weighted average. How do you find out the centroid of a body? Okay, so that's for a 3D body with some mass. What if it's a 2-dimensional body and you have to find out centroid, not center of mass, centroid? How do you find out the centroid? You are right about the mass part, center of mass. Just tell me in 2D. That was for 3D. So what about 2D? A 2-dimensional body has no mass. What does it have? Just give it a minute, try thinking about it. It's very analogous to the center of mass. For centroid, what properties do two-dimensional bodies have? We can't just do c bar 1 plus c bar 2 by 2 because this body can be any shape, right? So what defines its shape? What property will change with the change of shape? Area, yes. So it is c1 bar into s1 plus c2 bar into s2 by s1 plus s2. If it is center of mass, we will do m1, m2, m1 by m2. Okay, this is centroid. So we find out c1 bar that way. So yeah, c1 bar, and then the overall x AC. So this is your c1 bar, but we need its distance from the leading edge as a line denoted by in blue. So we find that by 800 minus c bar plus c bar by 4. So c bar is the mean aerodynamic chord, c bar by 4 is the location of the aerodynamic centers, that is this. And distance from the leading edge is the sum of this green line plus this purple line. Purple line is c bar by 4, green line is 800 minus c bar. Okay, so you found out c bar aerodynamic center. Now let's find out a few quantities. What they've asked you to find, they've given you this graph of CL versus alpha of the airfoil. So now they've asked you to find out CL naught, CL alpha, CM naught and CM alpha. So how will we proceed with this? How will we proceed? All of these terms, CL naught, CL alpha, CM naught, CM alpha. Okay, so let's just take 0.1. Okay, let's just take 0.1. CL alpha. Yes. So just take an approximate value. Just let me know. So it will be. Let's just take these 2 points. So that will be 1 minute. Let's take a fairly straight line. Okay. Okay. So just tell me something around 0.5 by almost 0.5. Let's just take 0.4748, something like that. Just approximate. You can do it properly when you're given the graph, but let's just take an approximate value. Is this fine? Just tell me if it's not fine. Okay. Sorry? Okay, so it will be 5, right? 5. 4 point something. It will be 4 point something. 4.8. Okay. Now it's fine? Okay, so approximately. Okay, so this won't be 0.5, it will be 0.49 or something. So how much will this come to? 0.5 divided by 4.8 is 0.104. Okay. So one thing you need to keep in mind is when they give you this graph, it's the graph of the airfoil, unless explicitly specified that it's the graph of the wing. Okay, so these quantities are for the airfoil. So this is CL naught, or you can say this is CL naught 2D and this is CL alpha 2D. But we need to find out 3D. Okay, for CL alpha we have a straightforward formula. CL alpha 3D equals CL alpha 2D by 1 plus CL alpha 2D by pi EAR. What is CL alpha 2D is 0.104. 1 plus 0.104 by pi, take E as 1. And what was aspect ratio? This was your structure. What was the aspect ratio? Yes, so how do you find out the aspect ratio of the overall structure? Okay, Okay, so any term. Okay, so you can use a similar weighted averaging technique for aspect ratio. Okay, so what we can do is that aspect ratio is AR1 S1 plus AR2 S2 by S1 plus S2. For any such term of a combined figure, you can use this weighted averaging technique. Okay, so let's just substitute these values and find out. AR1 was 1.23, S1 is 368330.9, plus aspect ratio 2 is 3.36 into what is S2? Yeah, 13543.75. 13543.75 divided by the sum of the areas. Okay. So how much is this coming to? 3 areas, so it is 3, 6, 8, 3, 0, 1 plus 1, 3, 5. So I'm getting 1.8. So I substitute that here, and the CL alpha 3D is. Can you just calculate and let me know? What is the CL alpha 3D? What is CL alpha 3D? Will it be that less? No, no. Just calculate it again. It will be somewhere around 0.104 itself. Okay. So it's 0.102. So we found out the first quantity, that is CL alpha. What about CL naught for 3D? How do you find this? Okay, you don't have that formula. That formula doesn't, it's not the same. So how do we do it? So what we do is that both of them are linear approximations. Okay, so so you take CL naught 2D minus 0, that is at 0 CL, like CL versus CL, CL versus alpha graph, 0 CL. So where it is CL naught, you have 0 alpha, and where 0 CL, you have alpha L equal to 0. These are the 2 points, right? So if you have some graph like this, I take this point and I take this point, and I take the slope between both of them, right? So this is CL alpha 2D. Similarly, for a 3D case, you have CL naught 3D minus 0, by 0 minus alpha L equal to 0. This is CL alpha 3D. Okay. So what you do is you find out alpha L equal to 0, which will be same for both 2D and 3D, because when it becomes 3D, all that happens is it moves like this. This point remains same. Okay, this is for 2D and this is for 3D. Okay, your alpha L equal to 0, that point remains same. And the aspect ratio changes from infinity. This is aspect ratio equal to infinity. This is aspect ratio equal to some quantity. Okay, when it reduces, the slope reduces, but this alpha L equal to 0 remains same. Right, the angle of attack at which your lift is 0 remains same. So from this equation, find out alpha L equal to 0. What is the value? So it will be a negative quantity. Huh. Okay, let's just take it. It's coming to around 0.9. It's not exactly 1. So, okay. Negative 0.99. Okay. Let's just take that. Substitute that here and find out CL0 3D. CL0 3D will be CL alpha. This is 1. This comes to point. Okay. 8 into 122. So it's coming to 0.01, right? CL0 3D is 0.01. Okay, so this is your value, this is one quantity. We have found out these two. How do we find out CM0 and CM alpha? Given that, okay, question has a couple of values. Yes. Yes, that's all, that's all. Is it 0.10? Oh yes, it's 0.1. So it will be 0.09, something like that, right? It will not be point. Okay, that is not right because it has to be less than the CL0 2D. Right? It is reducing. The CL0 is reducing. It has to be less. Yeah, it has to be less than 0.1. Okay. Yeah. So yeah, let's move on to CM0 and CM alpha. The question has the static margin is given as 10% and your CMAC is given as 0.01. Given these quantities, how do you find out CM0 and CM alpha? Okay. CG minus X bar AC. Okay. How do you find this? CMAC is 0.01. CM alpha wing is, it's not CM alpha, it's CL alpha, right? CL alpha wing was 0.102 and then How do you find this? How do you find XCG? Yes. So static margin is, okay, so this is your aircraft. What is the neutral point of this aircraft? Have we found that quantity somewhere? This entire structure is your aircraft, okay? There's nothing else to it. This is it. This entire thing is your aircraft. Exactly. Exactly. So AC is the neutral point. Static margin formula was x bar NP minus x bar CG. Now NP is nothing but AC. So x bar AC minus x bar CG. So it will be negative of the static margin here, right? It will be minus. This quantity is minus static margin. Minus static margin. Correct? So it will be minus 0.1. Yes? Is there a confusion? Okay, okay. What is the value of Cm naught? What is the value of Cm naught? Wait a minute. What is the equation for Cm naught again? Cm alpha plus what is this quantity? It should be Cl naught, right? Yes, so this is wrong. So the Cl naught 3D is 0.09. Now calculate and let me know. Okay. Will it come to the same quantity? Did you try it? Yes, it's coming to the same quantity, 0.09. Okay, so you can either follow this method or use an empirical formula similar to this. Okay, so the value we get is 0.09. What about Cm naught? What is Cm naught? Okay, correct. And then Cm alpha. What is the formula? Yes. So what is this coming to? C alpha of the wing is 0.102. So is the aircraft stable or unstable? Not 0002? is 0.001. Cm alpha is, okay, so is the aircraft stable or unstable? Stable, yes, because your Cm alpha is negative. You don't require any other thing to characterize longitudinal stability. Okay, you can also see that the static margin is positive, so yes, it has to be stable. Okay, now let's just go over some derivatives. So we had discussed this in the previous class. I'll just ask you randomly, what is Ch alpha, positive or negative? Ch is the hinge moment, alpha is the angle of attack, positive or negative, Ch alpha? Negative, yes. Can you justify your answer? Let me just draw that. Correct, so this is your hinge. Yes, so positive alpha generates a positive lift, there is a negative hinge moment, so Ch alpha is negative. Okay, next Cm delta E. Cm delta E is also negative, correct. So if this is your tail and I deflect the elevator down, elevator deflection downwards is positive, okay. Let me just write that. Delta E positive is down. This is the convention that we follow. Okay, if I deflect the elevator down, again produces a lift upwards, produces a pitch down, nose down moment. So Cm is negative. A positive deflection of delta E, you have a negative pitching moment. So Cm delta E is negative. Okay, dCm upon dCl for a stable aircraft, negative, correct. So your graph is something like this, Cm versus Cl or Cm versus alpha. Only thing that you need to remember between these two graphs, that is Cm alpha, is that this intercept point is not the same. This is Cm naught and this is not equal to Cm naught. This is another value. Okay, it's not equal to Cm naught. That is something that you need to remember. We had done a couple of problems on this. Okay. Okay, now let's. Yes, both Cm naughts are not equal. For a symmetric airfoil, it will be same, but as a general rule, don't take it equal. To be on the safer side, they are not equal. Your Cm alpha, when it's just Cm naught, when they refer to Cm naught, it is this Cm versus alpha Cm naught, not the Cm versus Cl. Okay. So when they say Cm naught, I think unless explicitly mentioned when it's Cm naught, it's always related to the Cm alpha curve. Okay, and these two quantities are not the same, they are different. It will be same only for the symmetric airfoil. Okay. Okay, now let's see another quantity. Cl delta E. Cl as in a coefficient of lift, okay, of the change in the lift of the aircraft. Cl, coefficient of lift of the aircraft. If I deflect the elevator down, this case, you have an increase in the lift rate. This is your delta L, correct? Because of a deflection of the elevator, there is a change in the lift. Correct? So it will be positive, right? If I deflect the elevator down, there is an increase in the lift. Okay? overall lift if I have after some time, right? So when this lift is produced, so the equation for CL delta E was eta VH, and there was tau, but all the quantities were positive, there was no negative sign. So this delta L dCl by d delta E, if I produce lift here, if I produce lift here, it doesn't matter, right? The lift is increased. Not just the tail lift, the overall lift of the aircraft at that point is increased. Yes, lift of the aircraft. There is a change in the lift produced in the aircraft which is positive with a positive deflection of delta E. Okay, so this is positive. This is not the exact equation. So this is positive. Okay, now d delta E by dCl at trim. This equation, do you remember, d delta E by dCl, or the delta E equation at trim? How much elevator deflection is required at to trim the aircraft at some CL? This is at trim. This equation was 1 d delta E by dCl into CL trim. Do you remember this equation? Yes, it will be 0 at neutral point, but in general, for a stable aircraft, d delta E by dCl, this okay at trim. So this is how much delta E is required to trim the aircraft at trim. So if I deflect the elevator, it's not at trim, right? Yes, so how much elevator is required to trim the aircraft at CL trim? This is your equation. Correct? So this quantity will be positive or negative. Do you remember this equation? What was the expansion? That slope was x bar. It is 0 at neutral point. You are right. X bar np by x bar cg by what was the denominator? Cm delta E. Now this is positive for a stable aircraft. What about Cm delta E? That's another quantity. Yes. Cm delta E is negative. So your d delta E by dCl at trim is negative. Right? Okay. Then let's do the other hinge parameters for sake of completion. Ch delta E. Negative, yes. So we saw that positive angle of attack produced a positive lift and which produced a negative hinge moment. Similarly, if I deflect the elevator down, that is positive delta E, again you have a positive lift generated, again you have negative hinge moment. Ch delta E is again 0. What about Ch delta T, where delta T is trim tab deflection? Again negative. And the reasoning is the same. Okay. Then what else is left? Cy beta. Cy beta. Y is the side force. Okay. So let's see. This is your. I cannot put that in this direction. So this is your fuselage reference line, and you have your vertical tail here. Okay, CL beta CL as in the rolling moment. Okay, yes, that is positive. What about C by beta? Side force. Y is side force. So this is your positive or negative beta? Yes, positive beta. So it's this is the angle that is seen here. It generates the force in this direction, right? But our sign convention, positive y axis is in, this is your positive y. Yes, then it is negative. So Cy beta is negative. For a positive beta, you have a force generated in the negative y axis of the aircraft. Cy beta? dcy by d beta, that's all. Like we did, where did we do? We did this CL delta E, we do CL alpha, just like that. How much side force is generated with a positive side slip angle? So the aircraft overall experiences a side force in the negative y axis. Okay. So now, along with this, let's just do Cn beta. If this is your CG, positive beta produces negative y, produces what kind of moment about CG? I told you this is the CG and this is your AC of the vertical tail. So what kind of moment, as in the yawing axis? Cn, yawing moment. Positive, exactly. So it will be something like this, and that is your positive yawing moment. So Cn beta is positive. Then what is left? Cl beta, where L is the rolling moment. Is it positive? It is negative. So you have, how do I represent this? So if you have your vertical tail here, and you have, how do I do this? Okay, let's just see. So you have your aircraft here, and this is your vertical tail. It rolls the aircraft in this direction, right? If you have a force here, it rolls the aircraft like this. So it is in the negative rolling moment. So this is negative. Yes. Rolling moment due to positive beta is negative rolling moment. Okay, so you will have a rolling towards your left. Okay, then what else is left? Let's CL delta A. Delta A is positive aileron deflection. Positive aileron deflection is what? Right wing aileron goes down, left wing aileron goes up. That is your positive aileron deflection. Let me just write that. Positive delta A is a right aileron down, right aileron up, left aileron down. So that means your right wing goes up or down. Right wing down. Yes, this is right rolling. This is positive rolling moment. Okay. So CL delta A will be positive. Yes. So for a positive deflection of aileron, the aircraft rolls towards the right. So that is positive. By convention, rolling right is positive. So CL delta A is positive. Okay. What else is left? I think we've covered all the parameters. Cn delta R. Cn delta R. Before that, let's do Cy delta R. What will it be? And rudder deflection towards the left is positive. So if I deflect it this way, this is positive delta R. Delta R. yeah, correct, it's positive. So this is positive. So if I deflect the rudder here, side force is generated in this direction, which is positive y. Correct. Now what about C and delta R? That is the yawing moment for a positive rudder deflection. This rudder deflection produces a positive y. What yawing motion does positive y produce? Yes, negative. Negative, yes. So I think we have covered all of those derivatives. Yes, we've covered all of the derivatives. Okay. So with this we end today's lecture. Do you have any questions? Any doubts, any questions? Yes. Assignment 12 we'll discuss on Tuesday. Okay. So anything apart from that? Okay. So then we'll end this here. You can leave. We'll meet on Tuesday and we'll discuss assignment 12. Thank you for joining.